flying the space shuttle, and you notice that it's moving kind of sluggishly, and then you look up at the panel up here, and you notice that, oh, we've got a barber pole on one of the aft RCS isolation manifold talkback indicators. And now, so you understand that why it's acting sluggishly, but then you got to wonder, wait a minute, what happens if one of the valves is open and closed, or one's open and one valve is closed, and when you're actually trying to move the shuttle with the rotational hand controller, that it's actually using the oxidizer, it's kind of venting it out overboard. What are you going to do? Well, this week we're going to talk about that, and also we got a shout out to Strike Raid, who actually he was and worked for NASA as a reaction control system engineer, and then as a site coordinator for the shuttle. So yeah, those kind of guys actually listen to us, and correct us. So later on in this issue, I'm going to go over what he said that might be, would help correct me on some misunderstandings that I had with the system. But first, let's talk about the aft RCS manifold isolation switch, how it works, and why we might use it on the shuttle. And it takes you to the aft RCS manifold isolation switch, and these are the manifold switches as we have here, and what they do is they control a pair of valves, one fuel and one oxidizer, which allows the propellant to flow to the jets on the corresponding manifold. Okay, and these valves are between the tank and isolation valves and the forward RCS jets. So what the switch is going to do is actually cut off the flow of the oxidizer or the fuel to the jet. So let's say, let's make it easy. Let's go over here. We have on the left aft RCS manifold number 1 here, we notice that we have for the left jet, we have one all the way through here for the shuttle to go left, up, or aft. Okay, so those positions, we notice that is sluggish. So we think that it might be leaking fuel. Well, there's 3 positions here. There's open, GPC, and closed. Open, you open up that manifold, so it automatically goes right through the manifold to the jet. You have the GPC, the general processing computer, and the computer will determine when to open that valve. And then you have close, which just cuts everything out, so nothing is able to flow, not fuel or oxidizer. So here, if we have it's being a little sluggish, we know that from the talk back that this is the problem. Then this, we might be having one oxidizer or the fuel might be open while the other one is closed, and every time the computer or the astronaut is trying to move the space shuttle left, up, or aft, it's leaking out oxidizer. So you're not getting any, well, you're getting a little force because it's jettison that oxidizer, jettison the fuel, whichever it is, but you're not getting the real amount of thrust. So you cut that off, you make sure that it's not leaking, and then the other thing it does is the oxidizer, the fuel that was going to there, would be left over for the other jets here. So we want to go left, and we see we have 2 and 3. Well, the oxidizer fuel that would have been in this jet, in the 1 jet, it would go to the 2, 3, 4, or 5. So it would be distributed to this these jets here. And what it's doing is it's making up for this one. These jets, because it lost one, you lost 1/5 of your power, so it might stay on a fifth longer to try to make up for that thrust that is lost here. So that is what that switch does. Now, to get to what Strike Raid was telling me about this is we're going to go into general. And because we come down here to the jets, and we're going to go in to look at here. This is perfect. Okay, so you see you have the helium up here, and it comes in and it goes into the oxidizer. But what it does, this helium, I thought because it was an inert and I couldn't find it on the diagram, that it mixed with the oxidizer to push it out. That is wrong. The oxidizer and the fuel, they have a bladder around them. And what the helium does is it comes in and pressurizes on the backside. And why that's important is because, well, when we start getting close to the using up the oxidizer, let's say we use 20%, well, that means that there's less pressure. But if we have all the helium here pushing on it, it's a kind of it's keeping the pressure behind this oxidizer as high as it should be. And why is that important? Because that is pushing the oxidizer into the jet. And if the pressure is low on the oxidizer or the fuel, the mixing is not going to be the same. So, or is not going to be, it's not going to be the same. So it's not going to be as efficient. And because it's not as efficient, you'll be wasting oxidizer and fuel. So this system here, which is the pumps basically to push the oxidizer and the fuel, that is trying to stay constant with the helium pushing on the backside of a bladder, sort of like squeezing a balloon. Like if you want to get the last of the air out or you want to get more pressure out, you squeeze a balloon. That's what this helium is doing for the oxidizer and the fuel. So that is what what Strike Rate told us, or told me, to pass on to you, and I thank him for that, and I thank him for being a viewer. Now we are going to go look at more on the schematics of the left and right aft RCS isolation valve switches, or manifold isolation switches. And it's for our Patreon members who, if you pay for it, which is like $5 a cup of coffee, or if you are a free member, and it doesn't cost anything if it's free. You just sign up and you will go over the schematics. And when you click on the schematics, it takes you to the schematic of the reaction control system. And here we see the aft reaction control system diagram or schematic. And we are talking about this manifold, this part right here in the manifold isolation switch with the manifold down here. So this switch is controlling what goes into this manifold. And as you can see, well, as I've told you, there's two lines here. This one line is actually two. One is fuel, one is oxidizer. It comes through where this manifold isolation switch is, through that valve, and it allows the pressure to go, or the fuel and oxidizer to go into the manifold. Again, separate lines. They each go to one side of the thruster, and in the manifold, and from there they mix in the thruster and produce thrust. So what the manifold isolation switch is doing is, if for some reason there is an oxidizer and fuel, but the oxidizer isn't open on one side and it is on the fuel side, you're not leaking fuel out this side. It's or you'll be leaking fuel out the side, so you want to close that manifold switch as we shown before, and that saves the fuel, and in this case for the other thrusters, to compensate for this all the P1 thrusters that you have lost. And you can see we have the pressure down here that's showing you which pressure, or that the pressure is, there is pressure on the oxidizer and the fuel for both sides, and that comes up in the talk back indicator that's above that switch that we see. So that is what we're talking about. Also, to go back to what Strike Raid was talking about, who was, like I said, the RCS system engineer, and then also a site coordinator for the shuttle. The helium here, this comes through and it goes into this tank, but the tank has a bladder around, sort of like there is a balloon on the inside with oxidizer or fuel, and the nitrogen comes down into here and it fills around that bladder, pushing down the oxidizer into the manifold down here. And the reason why we do that, why they have that, the helium doing that, is because it's actually giving a constant pressure, as you see right here, and you need a minimum pressure to go into the thrusters so that you can monitor the amount of fuel or oxidize, or not monitor, but have the right proportion of fuel and oxidizer at the jet. So if you are a paying subscriber, and that is for $5 a month, it's basically a cup of coffee at Starbucks, 1 cup of coffee. We're going to go into more information about this. So if you click on General, it takes us to the General page, and we are going to come down into this diagram that we had before and go past the schematics. And okay, so we were here, and we the isolation valve with 5. This is a very unique manifold, and the reason why it is you can see here on 5 there's only 2 jets, and so this right here, there's only 2 where the others have 3. And the reason why we have to go back up is because those are what we call, hang with me, they are a specific thruster called the, here it is, the vernier jet. And this it works like the primary jet, except it has less thrust. Now, the reason why it has less thrust, this is for fine-tune maneuvers. If we go up to the diagram and we look at 5, you see how we have 5 here and 5 here. Okay, so what these jets are doing is for small movements. So if you lose those jets on your manifold, that means the shuttle's going to respond a little bit more. It's not going to have the finesse that it would have. So that would matter when you're trying to dock with the shuttle. You'd have to be a little bit more careful, and the same thing with the computer. The computer might be a little bit more jerky, because if you isolate, you take those out, you're going to lose the ability to gently move the spacecraft to left, right, on and up for the shuttle. So that is all for this week. Again, without you, I could not do all of this, and I hope you enjoy it. And because of your involvement, we got someone who was a reaction control system engineer for NASA and also a site coordinator for the space shuttle that is watching us. And it was because someone out there, you promoted it, and that is just amazing. And then you've got the other people that have come to help support us, and just like you do, and that keeps me going. And not just moral or on well, on the spiritual side of the space exploration, but also financially. You keep all of this up. And for that, again, I thank you.